For those not here, this is recorded, just be aware of that. So the atmosphere topic is one where you've said to me, this is a topic you're a little bit worried about. It's an important topic for paper 2. It's not the biggest topic, but people usually find it quite hard to do well in the topic, largely because they don't necessarily go away and learn it. There is quite a lot of sort of fact-heavy stuff. But so we're not going to try and teach it, reteach everything in detail from scratch. We're going to go through the kind of key points. But you have to have the idea that the early gases around the Earth's atmosphere came from volcanoes spewing those gases out. And you have to be really clear that primarily the early atmosphere was very heavy in carbon dioxide and water vapor. So water vapor, so they're the key things that we need to be aware of. There's a little bit of sort of how science works in that, isn't there? Because how do we know what gases were present in the early atmosphere of the Earth? Well, we don't really. These are theories based on looking at the geology of rocks, probably, and all sorts of things, but also looking at moons and other planets in the solar system, looking at what they might look like. Okay, so what we know from atmospheres that are very heavy in carbon dioxide and water is that those atmospheres are extremely hot. Venus being a really good example. Okay, so the early atmosphere had high levels of carbon dioxide and were very hot due to strong greenhouse effect. There may well have been nitrogen in there in the atmosphere as well. But nitrogen is not one of the gases that we sort of spend much time thinking too much about. What we do need to think about is what happened to those gases and how they've changed over time, and how we've ended up in the atmosphere that we've got today. All right. So the key thing really is that over time, you know that the early Earth was extremely hot. It was a hot molten planet originally, and cooled down, solidified, and as it continued to eventually cool down, it cooled down enough that the water vapor condensed. To form the oceans. Oops. So you can kind of have this idea in your head of the water vapor literally raining for probably tens of thousands of years, and enormous quantities of water were left on the surface of the Earth. Now that allowed the planet to change in lots of ways. Right, the fact that the oceans were formed meant that we've then got liquid water on the surface of the Earth, and scientists are pretty convinced that liquid water on the surface of a planet is essential for the evolution of life. You don't need to know the numbers here, I would say, but I'm getting this from a book. It's saying that life began, people think, somewhere around 3.4 billion years ago. So, well after the oceans had formed, life began. And eventually, about 2.7 billion years ago, those living organisms started to change the chemistry of the atmosphere. So a kind of algae developed which was able to undergo photosynthesis, and therefore it would be making its own food through photosynthesis. You know about photosynthesis in detail from biology, but that meant so there's a key word there for you to get in. That meant that carbon dioxide levels in the atmosphere would start to decrease as carbon dioxide was being absorbed and used in photosynthesis. It's also worth pointing out at this point that carbon dioxide levels went down due to absorption to the oceans as well. So carbon dioxide reduced due to photosynthesis and dissolving into oceans. It's quite small, hopefully it's big enough to see. Because of photosynthesis happening, you know that photosynthesis is carbon dioxide really being used to make glucose, but the byproduct of that is oxygen. So oxygen levels increased. So the atmosphere started to change. And over the next billion years, it's talking about in here, the levels changed, and eventually plants developed and became more and more developed, and we ended up changing those quantities quite significantly. Let's recognise then the atmosphere has changed a fair bit. Carbon dioxide levels have come down, oxygen levels come up, and also we need to know a little bit more about what happened to that carbon dioxide. So dissolving into the oceans, I really want you to get the idea that the carbon became, and the key word you need is locked up. There's a whole bunch of ways that carbon can be locked up, and I don't want to get into too much detail here. All of that was covered in your lessons last year. But places that can be locked up are fossil fuels. So think about plants, as we talked about in a previous lesson, plants being squished, compressed, and turned into fossil fuels. So those fossil fuels will particularly be coal, enormous amounts of coal, and crude oil. Right, so the carbon atoms that were in the living things from millions of years ago got compressed under huge temperatures and pressures. Millions of years ended up forming fossil fuels, right? And we now are gradually burning our way through those and returning some of that carbon back to the atmosphere, which is great news for everybody, right? And also, and again, I'm not getting into the detailed processes here because I don't need you to really, but when you dissolve carbon dioxide in water, you form hydrogen carbonate and carbonate ions, and eventually you end up with carbonate rocks. And some of that can come from the skeletons of living things too. So carbonate rocks. So by that I mean calcium carbonate, so chalk, limestone. And think about all of the, just around here, think about all of the chalk cliffs that there are. Imagine how many millions and billions and trillions of creatures would have need to have been died, squished together and end up there, and how much carbon is locked up in the rocks around where we live. Enormous amounts of that. So we've got fossil fuel and we've got rocks locking up that carbon. That is not a lot of detail there, but the key point is made. All right. So that through those kind of processes, we've ended up changing the early atmosphere to what it is today. There's one more process that I'll cover, which is that ammonia, which was produced. I'll go back to the top there and mention that ammonia was the gas. Ammonia is something we need to know about, isn't it, for the Harper process too. But ammonia was one of the early gases, and it's thought that ammonia may well have reacted with the oxygen that was produced from photosynthesis to turn into the nitrogen, so some more nitrogen was produced and water. One thing to say about nitrogen, it's really unreactive. So the nitrogen that was in the early atmosphere from the volcanoes and the nitrogen that was produced from the reaction with oxygen and ammonia, any of the nitrogen that was produced, it's probably just still sitting in the atmosphere, which is why such a large proportion of our atmosphere is nitrogen, because it really doesn't do very much. It doesn't react very much. Okay, so there are some things that it does, but it's quite unreactive, and that's really thought to be to do with the fact it's got this very strong bond that makes it kind of stable, this triple bond that you've just drawn when we did our little breakout. Right, so I'm sure you know this, but the atmosphere today, you must know this, is 78% nitrogen, roughly, 21% oxygen, roughly. Argon, which is again an unreactive noble gas. Noble gas is unreactive, full outer shells, all that stuff. So that's persisting as well. So the nitrogen persists in the atmosphere, the argon persists in the atmosphere, and not much changes. They more or less add up to 100%. But there are small amounts of other gases, and the key one that you really need to know, of course, is carbon dioxide, which is a greenhouse gas, and the levels of that are currently around about 0.04%. Whoops. 0.04%. Now that is an important number because it's climbing. We need to understand that that level of carbon dioxide means we've got a greenhouse effect happening, which is a good thing, and we'll talk about that in a minute. But too much carbon dioxide can cause problems, as I'm sure you're aware, which again we'll talk about in a moment. So, yeah, so again, just remind you, again, this is sort of partly for those not here and listening. It's a little breakout on bonding again. Make sure you're well practiced on drawing, describing the structure and properties of simple covalent ionic substances, and we'll do metallic in a minute as well. Right, so the greenhouse effect, I'm actually going to use the textbook picture here rather than draw it, because that just takes too much time. You've already got this drawn, right, in your notes. I don't want you to sit and draw this again now, but I want to talk you through the processes, and what we might do is just write down the key steps that are going to get the marks in an answer for this. Right, so usually I find when reading answers to this, the quality just isn't quite high enough to get all the marks. So I'm going to give you a really clear thing that they're looking for when explaining what's going on here. So we've got to talk about, in the end, we'll talk about the infrared radiation being trapped in the Earth's atmosphere and therefore trapping heat in the atmosphere. And I often start, when I teach this to the lower school, talking about is it a good thing or a bad thing, the greenhouse effect. Of course it's a good thing. Without the greenhouse effect, the Earth would be as cold as the moon. And the moon is very cold when there's no sun blaring at it. Right, so we need the greenhouse effect to be a planet where we've got liquid water and it's warm enough to survive. The problem comes, as we'll see in a bit, when we've got high levels of greenhouse gases. But what's going on? What is the greenhouse effect? How does it work? We need to know the sun beams out lots of radiation, and in particular we need to be aware of the short wave radiation that's coming from the sun. In particular, the UV and visible light. The reason that those frequencies are important, and this is something you need to get clear in your answer that we'll write down in a second, is that those wavelengths of light are able to pass through the atmosphere. That's often missed in answers. They pass through the atmosphere, they're not absorbed by the atmosphere largely, and they hit the surface of the Earth and they cause the surface of the Earth to warm up a little bit. When things get hot, you know from infrared cameras that you've seen pictures from, the Earth will, or hot things emit infrared radiation, heat. And that infrared radiation is being sort of shown as the upward arrows here. Some of that will just pass back through the atmosphere into space, but some of it will be absorbed by the greenhouse gases, in particular carbon dioxide, because there's a large quantity of it in the atmosphere, water vapour, the levels of which are changing all the time, and you know about the water cycle, and increasingly levels of methane as well. Methane is a very powerful greenhouse gas, though there are quite small quantities in the atmosphere at the moment. They absorb the infrared radiation, then they re-emit it. So they absorb it, they get all excited, and they re-emit it again. Right? So we need to go through that process properly. So the greenhouse effect then, what do you need to say in your exam? I'm not going to draw the picture for you. So first thing, short wave, or high energy if you like your physics, the short wave, so UV or vis, light from sun, passes through the atmosphere. That's the mark that most often is missed, I would say. The surface of the Earth then absorbs that radiation, and the surface of the Earth is therefore heated. That now slightly hotter surface will emit infrared radiation, emit heat. Some of that then just passes into space, through the atmosphere into space. Some, and this is where, again, the key mark, I think that people really don't score well enough, and you can, it's easy, you're all capable of it. Some is absorbed by greenhouse gases. And you should know that they are carbon. It's not just these, there are other greenhouse gases in small quantities as well, but these are the key ones. Water vapour, and increasingly methane. We know that methane is produced by cattle in particular, and some other processes as well, decomposition, things like that. Then, this is where it's important, then emitted in all directions. So some heat is trapped. That feels to me like a 4-mark question that should be a banker for everybody, I would say. If you can learn that, if you can turn that into a flashcard and learn it. Right. What I'm not going to spend time on, because I don't want to patronise you too much, is we all know that carbon dioxide levels are going up, and we know why. So burning fossil fuels, for example. So don't say because of cars, because some cars don't burn fossil fuels, right? Particularly these days. But burning fossil fuels, or petrol, or factories producing or using lots of electricity, so methane maybe is burnt in the power stations or whatever it might be. The fossil fuels being burnt increases carbon dioxide levels, and then there's all the consequences of climate change. Now, forgive me for not writing these out, because you know them. If I asked the year 7s, they said know it. Ice caps melting, sea levels rising, increased extreme weather. You know all this stuff, right? Just nod confidently, you know all this stuff really well. So forgive me for not just going over that. Right. You have to have the concept of the carbon footprint. And again, I'm not going to go through this in detail, but I want to take another breakout before we do this. So a little breakout on metallic bonding. So could you describe the structure of aluminium and talk me through its properties, in particular its conductivity, melting point, and electrical conductivity, thermal conductivity, and melting point. Go. Definition of carbon footprint is there in bold. That's a definition to learn, isn't it? Total amount of carbon dioxide and other greenhouse gases emitted over a life cycle of a product. So can you make a note of that, those 2.5 lines there, please? Just bullet point it, summarise it in your own words. Some people take longer to write than others, so if you've done that quickly, let's consider ways of reducing carbon footprint. And I think we know, again, what these are without too much difficulty. A couple of which are written underneath in the book here. Put this down. Yeah. So ways of reducing carbon footprint would be? Yeah, so using public transport rather than driving, car. Another one, please. Locally sourced produce. Good. So stuff hasn't got to be transported around the world. Another one, please. Yeah.
Reduce, reuse, recycle.
Anything to do with reduce, reuse, recycle. So I've discovered Vinted this week and I'm very excited. So I bought using sort of stuff that people are going to sling away, but it's perfectly good and it's barely been used. Reusing, reducing, and recycling are the things they want you to talk about. All right, let's move on from that. I'm not going to get into all of the reducing carbon footprint stuff. That's all Key Stage 3 level, I would argue. You can do that. So let us then concentrate on where I think there's more difficulty, which is around the things that we're throwing into the atmosphere. So let's talk about the very, very briefly hydrocarbons. So C, N, H, I don't know, let's call it M. So hydrocarbons, when you burn them, you can get complete and incomplete combustion. So this is really part of the crude oil topic, but it links, doesn't it, nicely to this. So you get carbon dioxide, carbon soot, carbon monoxide, as well as, of course, and people often forget this, you get water produced when you burn stuff. So complete combustion, of course, you only get fully oxidized carbon, which is carbon dioxide. But if you've got a lack of oxygen, insufficient oxygen, you get soot produced and carbon monoxide produced. So carbon dioxide, of course, is linked with climate change, or the enhanced greenhouse effect, if you like. So too much carbon dioxide in the atmosphere and all the consequences of that. Soot, or amorphous carbon, if you like, is linked to global dimming. These are all kind of one markers, but you need to know them. Carbon monoxide is toxic, and ideally you'd have a sense of why it's toxic. It binds to hemoglobin. In red blood cells and stops them carrying oxygen around the body. But you do need to know that key word about carbon monoxide, that it's toxic. So there's a little bit on atmospheric pollutants. You wouldn't describe that as a pollutant. It does cause climate change, but soot and carbon monoxide are certainly considered pollutants. Okay. Let's move on though to other pollutants that we need to know about, and these are the ones that probably people find hardest to remember and probably need the most amount of work, which is why I'll spend a little bit more time on it. So if you're burning a fossil fuel, it burns at a really high temperature. It's a hugely exothermic reaction. And by the way, we'll do some stuff on energy changes probably next week, but it's highly exothermic because you're forming some very strong bonds in the carbon dioxide, and that releases loads of energy. And that's great for making your cars powerful and all the things that they can do. But the fact they're at a high temperature means that a reaction can take place which wouldn't take place at normal temperatures. So this isn't a direct consequence of carbon burning, but at the high temperatures of say a car, diesel car, or a jet engine, particularly high in the atmosphere, nitrogen and oxygen that are in the atmosphere at 78% and 21%, as we discussed earlier, will react with one another to produce what we call nitrogen oxides. So I'm just going to write NOx, nitrogen oxides. There are lots of nitrogen oxides, so NO, NO2, N2O4, N2O, and so we simplify them just as nitrogen oxides like that. So only happens in the high temperatures of engines. So this is although it's not a direct consequence of the carbon in the fossil fuels burning, it's kind of an indirect consequence. This is obviously not a balanced equation, but you generate these nitrogen oxides. Now, they have a number of issues associated with them, and you might be asked what those are. One issue is that they can cause respiratory problems, in particular for people with asthma. There are lots of studies done in areas, say Birmingham might be a good example, or other big cities where you've got motorways travelling really close to, or major roads travelling really close to schools in particular, and the levels of asthma are really high in areas where there's people living and working, and particularly school kids being right next to these roads. It's why there are people, things like congestion charges are happening, people trying to find ways of reducing the nitrogen oxides produced by diesel cars, for example. So respiratory problems, asthma, I'll try and spell it right. But also, this is a little bit beyond the scope of the course, about the chemistry of it, but non-metal oxides can dissolve in water, and when they do, they form acids. What you do need to know, though, is that when the nitrogen oxide, that is a gas in the atmosphere, dissolves in water, it can go on to form acid rain. And the consequences of acid rain you're expected to know are things like fish, just general aquatic life, but also trees, and also damage. These are all sort of dying, death, and also other sort of slightly less concerning, I suppose, but limestone and marble buildings and statues, which are made of calcium carbonate, would become damaged over time. I'm trying to get the pictures of that here now. So they would react with the acid. The other one that people often struggle with a bit is this idea of getting acid rain from sulfur dioxide. Now, I want you to think really hard about what I'm saying here. This is not overly complicated, but people really struggle with it. So let's say you've got a lump of coal. There's a lump of coal, and I'm going to colour it in whatever colour that is, blue or black. Right? This person's got a yellow pen, but someone got a different colour pen. It's probably red or something. No, don't worry. Yeah, go on.
The black somewhere.
Right. So let's pretend that sulphur is red, which it's not. But in amongst that coal, not directly bonded to the carbon atoms in that coal, but also in there might be maybe 0.1% of sulphur atoms in there. Now, when you burn the coal, of course, which is mostly carbon, the carbon reacts with oxygen to give carbon dioxide, generates a load of heat, and we use that to power stations and our homes or whatever, although we don't use coal so much anymore. But the sulphur that's in there is also being burnt. It's at very high temperature, surrounded by oxygen, and the sulphur will react in a very similar way. And the sulphur will react with oxygen to give sulphur dioxide. And sulphur dioxide is also a gas, and the sulphur dioxide can also cause problems. So it's in tiny quantities, but they're significant enough when you burn lots of the stuff to produce issues. So the sulphur dioxide, so sulphur reacts with oxygen to give sulphur dioxide, and then the sulphur dioxide goes on to dissolve in water and is oxidized, and the process of that you don't need to know, so I'm going to brush over it, but you form acids. One of the acids you can end up with is sulfuric acid. The one that's more obvious to see is if you take water and sulfur dioxide, you can end up with a chemical called sulfurous acid, H2SO3. So these things are acids. So instead of the natural rainwater being about pH 6.5 or maybe slightly higher, but just slightly below 7 due to carbon dioxide dissolving in water, the pH can drop more due to these acids that make acid rain. So the gas dissolves in water droplets in clouds, and those droplets combine together to make raindrops. The raindrops fall on the ground then gets damaged. Minerals leach out of the soil, things like that, and plants and whatnot die. All right, so that's a pretty good place to pause for a second. The last thing that I'll highlight then is this sheet here that I put together to kind of help for you with making your revision notes on this topic. Basically, if you can answer all of those things, you're in a great place on the atmosphere topic. Really, you go back at your atmosphere test from year 10, and you'll find if you know the answers to all of these things, you'll be gold, you'll be sorted. Right? It's really not that big or difficult a topic, but it was usually one that people scored least well on. Okay? Hopefully that was useful. See you after school for the bonding session later on.